Welcome everyone to this online edition of the University of Toronto Where You Are series of events for alumni, which brings some of the University of Toronto's most compelling thought leadership to you, wherever you are in the GTA, across Canada, or in the world. Before I begin, I wish to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home of many Indigenous peoples from across Turtle Island, and we are grateful to have the opportunity to work and learn on this land. Today, I am delighted to introduce Professor Jessica Burgner-Kahrs as she delves into the research and application of advanced versatile robotics. The U of T Where You Are lectures provide our more than 630,000 alumni worldwide with stimulating and thought-provoking presentations from some of the world's top researchers, innovators, and teachers who carry out their work at the University of Toronto. We're fortunate to be able to attract top faculty members due to our global excellence and reputation and our location within one of the world's most diverse and dynamic city regions. For the second year in a row, the prestigious Times Higher Education's 2021 World University Rankings placed U of T first in Canada, 18th in the world, and among the top 10 public universities globally. And for the second year in a row, U of T ranks fourth in the world for the impact of its research papers behind only Harvard, Stanford, and Johns Hopkins. This recognizes our research as the best in Canada and counts us among the world's foremost universities by the quality of our research, putting us ahead of our peers at Oxford, Cambridge, and Berkeley. These accolades reflect the talent of our students and faculty, our impact on research and teaching, our interdisciplinary excellence, and our global reach. We usually present lectures like this to our alumni in regions around the world, but because of COVID-19, we've moved them online. This means that you can view these fascinating speakers from your internet-connected smartphone, and many more alumni can partake and learn about cutting-edge topics, such as modern robotics, which our guest speaker, who it now gives me great pleasure to introduce, will be speaking to you about today. Dr. Jessica Burgner-Kahrs is an associate professor with the departments for mathematical and computational sciences, computer science, and mechanical and industrial engineering. She's the founding director of the Continuum Robotics Laboratory and associate director of the Robotics Institute at the University of Toronto. From 2013 to 2019, she was with Leibniz University, and from 2010 to 2012 with Vanderbilt University. She received her PhD in computer science from Karlsruhe University of Technology in Germany. Dr. Burgner-Kahrs' research focuses on continuum robotics, in particular their design, modeling, planning, and control, as well as human-robot interaction. Her fundamental robotics research is driven by applications in minimally invasive surgery and maintenance, repair, and operations.
Thank you for the kind introduction, Barbara. Welcome, everyone. Welcome wherever you are tuning into my lecture on how we are rethinking robotics at the Continuum Robotics Laboratory at the University of Toronto Robotics Institute. Before I tell you more about how I am rethinking robotics by leveraging worms' tongues and elephant trunks, I want you to take a minute and think about what mental image comes up when I ask you, how does a robot look like? I guess some of you have been thinking about some robots that they have seen in movies. I put some on the slide. You can see Wall-E and Eve from the Disney Pixar movie, or Baymax from another Disney movie some years back. Those are great robots. They usually show what we roboticists would love to be able to do with our robots, but usually we're not quite there yet. In fact, most robots in reality do look like those robots on this slide. The majority of robots today, those up here, are used in industrial automation. They are used, for example, in automotive industry to automate tasks that are repetitive. There's also a huge area of service robotics. Biggest use case is logistics and warehouses, where these tiny robots here are carrying around goods to facilitate a faster logistic process. Some of you might also have a service robot at their home, a vacuum cleaning robot or a lawn mowing robot. And eventually, you have also come across some other service robots like surgical robots. This up here is a surgical robot system from Intuitive Surgical, which is used in a teleoperated mode, meaning that the surgeon teleoperates the robot from a console for laparoscopic surgery. And then lastly, there are some robots that are more human-like in their appearance. They have arms and legs and walk around, but those are only slowly getting into our realities. They are mostly still research and development. The robots that I've been showing you here are in fact not the robots that I'm working on. But before I'm going to tell you what kind of robots I'm working on, I wanted you to know about my favorite animal. Ever since I was a little girl, I loved elephants. I am really fascinated by elephants, particularly by their trunk. When you look at the motion capabilities of elephant trunks, it is quite remarkable. They are continuously bending structures. They can even extend. And while it's just their elongated nose, it is also their hand. They can use it to reach places hard to reach, like this elephant here. They can also use it as a hand or even as a weapon. Particularly the male elephants like to do this. And when you look at the motion capabilities, it is really, really remarkable how this elephant can use its trunk. Now, becoming a scientist, I was very curious about how this motion capability is achieved. And when I look at this skeleton of an elephant, what becomes very apparent is here, where the trunk would be, there are no rigid elements. There are no bones. There are no joints compared to the legs or to any other areas in the body. In fact, when we look at this plastination of an elephant from Gunther von Hagen's bodywork exhibition, we can see that the elephant trunk itself is composed of a multitude of muscle fibers, 40,000 to be exact. The elephant trunk is a muscular hydrostat, which enables the elephant to control groups of these muscles to bend, twist, and elongate. So it's only natural as a researcher to ask the question, can't we build robots with no joints in order to resemble similar motion capabilities? Isn't it possible to build a robot that acts like an elephant trunk and that can bend continuously, twist, wrap around objects, and reach places hard to reach? As it is in science, we all stand on the shoulders of giants. I have not been the first elephant enthusiast and roboticist asking this question. In fact, this area of continuum robotics research is quite about the same age as robotics is in general. About this first continuum robot has been developed in the early 60s that you can see over here. It was developed by two students, Scheinman and Leifer at Stanford University. They developed this pneumatic-driven continuum robot that you can see here, which is now on display in the Computer History Museum in Mountain View, California. They abandoned it because the movement was not very precise and it wasn't a great robot and it was quite short. But you can already see that in later research, this elephant never really left a researcher's mind, and they have been building all sorts of robots that are resembling elephant trunk-like structures. In fact, there's also some commercially available continuum robots that you can see over here, for example, from Festo or OC Robotics. These These continuum robots resemble pretty much the size of an elephant trunk, whereas this one over here is even longer. This continuum robot you can see over here is the longest available. It's 5 meters long, 3 meters of which can be actuated. But these continuum robots have a problem. Like, while they resemble the elephant trunk nicely, and they are certainly really amazing to watch, they didn't bring any benefit to robotics, particularly not to industrial automation, because the size and payload, so the size of the robot versus the amount of load it can carry, is really not that great. Like, this robot over here can only carry 3 kilograms of payload. Now, this doesn't go well with most industrial automation tasks. And that robot over here also has a pretty low payload. So there was really no advantage in building a robot that can resemble an elephant trunk, other than these motion capabilities being really amazing. These continuum robots do actually not help us in any of these tasks that I have on this slide here. Existing continuum robots and any other robot out there cannot really address what I envision them to do when I'm thinking about this elephant trunk and its motion capabilities. When I see this elephant trunk, I'm thinking of all sorts of applications which could benefit from something as dexterous as the elephant trunk. Any application that has limited accessibility. Any application, for example, in medicine, where you would like to reach a location deep-seated within the human body, like in the center of our brain or in the middle of our abdomen, like the kidneys. And I'm also thinking of, once I reach these locations on curvilinear path, how to manipulate at the site, do some inspection, for example, or some small repair, or a tiny little surgery. So while the elephant trunk is really motivating for me, the size is not. So the robots that I am working on are small robots without any joints. And these small robots without any joints are also continuum robots. I'm just interested in those that have a smaller diameter to length ratio. In the Continuum Robotics Laboratory, we are designing these robots. We build them from scratch in-house. And in doing so, we are facing a lot of design challenges. First of all, the design space to achieve these continuous bending motions, and also the compliance that we see in the animal kingdom, is quite large. Second, there is many different design paradigms that we cannot follow, because many of the design paradigms that we teach our engineering students are usually making use of rigid elements. And so having no rigid elements in a robot is somewhat unfamiliar to us designing these kind of robots. And lastly, while these 40,000 muscle fibers in an elephant trunk sound amazing, it's going to be really hard to control 40,000 instances of an actuator. So we will need to live with a finite control over these theoretically infinite amount of degrees of freedom. So how do we go about this? How are we designing continuum robots? Intuition could tell us, well, we could stick to what we know. We could stick to what works well. So we could stick to what we know from serial robot arms, just connecting joints with rigid links, a couple of revolute joints, all in series, and then making these links rather short, such that we have a discrete structure with motors in these individual links that could drive this snake-like robot. This is a good idea and has been helping in developing these larger scale continuum robots, but it doesn't really miniaturize well, because there's obviously a physical boundary in terms of how small you can make these motors and how small you can make these links. So rather than having a discrete structure, we are more interested in building continuous bending structures in order to achieve smaller diameters. One idea to do so is to, for example, use pneumatics and hydraulics and building a soft body such that when you pressurize it, it would undergo bending or torsion. We could also use shape memory alloys, shape memory springs, for example, that we could embed in a soft structure. And then by changing the temperature of this shape memory alloy, we could make the body also bend or undergo torsion. Yet these pneumatics and hydraulics, as well as shape memory alloys, are usually suffering from not so favorable dynamic and control challenges. So there should be another way to build these continuum robots really small, such that we do not have to face these challenges. An alternative to go about continuum robot design is to rather using intrinsic actuation, so embedding the actuation within the continuum robot, is to think about extrinsic ways to actuate the robot such that its body can be smaller. For example, in the discrete case, we could think about replacing these motors in these individual links by just tendon and wires that we route through and actuate at the back end. That way, we could make the body a little smaller. Yet, it would still be discrete, so not really continuous. So we would still be challenged to some extent. Building a continuous structure then would require us to also get rid of any of the rigid links and rather have a continuously bending backbone, a flexible material. And then we route, for example, tendons or wires along it that we terminate at different locations and also actuate at the end extrinsically. And ultimately, having a continuous structure which would not require any tendons anymore, that would be a telescoping tube structure. In the Continuum Robotics Laboratory, we have been innovating on a couple of those ideas over the past decade. So I'm going to show you some continuum robots that we have been building and also the scale at which we have been building them. The first one makes use of this tendon-driven paradigm, such that we have an elastic backbone in the center. It's a nickel titanium tube. And then we route tendons along its length. These red threads that you are seeing here are the tendons. And we terminate them at different locations to realize a segmented structure such that we can individually bend 3 segments of this robot. This robot's diameter is 7 millimeters, so rather small, and it can change its length from anywhere between 45 to 165 millimeters. With such a tendon-driven structure, we have a huge advantage. We can make use of morphological adaptation, which is an idea that also stems from biological systems that use their body to control basic actions. This robot we're seeing here, or any continuum robot pretty much, has a computationally powerful body in that sense that there are some encoded properties. This continuum robot you're seeing here, for example, can grasp or hold onto objects by just actuating and pulling on a tendon. And you can see by wherever this object or the finger of this user is, the robot can adapt its body to hold onto it. So it leverages its embodied intelligence, which is a huge advantage as these continuum robots are uniquely flexible. And in conventional robotics, this has been usually overlooked, that we could use that body to embrace its environment and make purposefully contact to hold on to something. That's a huge difference from looking at continuum robots versus rigid links robots. Now, the continuum robots we have been seeing on the previous slides were rather short. Just recently, we have been starting to investigate how we can build a longer yet lightweight tendon-driven continuum robot. And a very recent prototype that we have just built over the summer is visible here. It's an extensible origami robot. The idea here is that we use an origami body. So the body is completely made out of paper in an origami folding. Then we route tendons through it. So the whole structure is light as a feather because it's made from paper. And then there's just these tendons routed through it. And then in the center, there's still a nickel titanium super elastic thin tube such that we can actuate the lengths changing. And that way we could achieve a rather long robot, as you can see here. In full extension, it's 500 millimeters long. And as you can see here, it has the great ability, thanks to this origami inherent structure, that it can extend and contract rather fully, as you will see in a minute. So this robot can be as short as 58 millimeters. One inherent challenge that we have in continuum robots is that these robots are compliant, obviously, so they deform when they come into contact with the environment, which can be desirable, but in some occasions, it may also be desirable to stiffen the robot. And this is a principle I'm showing here. We have been working on a scale-like structure that we enclose in a silicone bladder, and then by drawing a vacuum, you can see that this sheath will stiffen in whatever configuration it's in. So right now we draw the vacuum, and then these scales are going to be pushed on top of each other, and the pressure causes them, thanks to the surface roughness, to have enough force in between such that we can stiffen the structure in any given shape, which could be cool to put around a continuum robot. Once it reaches its location, we can stiffen the structure up to have more stability to perform a certain task. Now, any of these continuum robots have been in diameter 7 millimeters up to 20. But I also want to show you world's smallest continuum robot that we have been working on over the past decade. This is a so-called tubular continuum robot. It only has a diameter of 0.5 to 3 millimeters. So you can see here it's composed of these super elastic tubes that are pre-curved. It's a shape memory alloy. Then they are used in their super elastic state, put inside of each other, and then we translate them and rotate them at their back ends to achieve this tentacle-like motion. This is the smallest we can do today. It's only it's a needle-like structure. You can probably imagine this being very useful for some of those applications I have been mentioning earlier, where you really want to sneak in to some place to perform a task. Now, I am quite sure that many of you have been wondering about how can we mathematically describe these continuum robots? How do we know how much tendon tension we have to apply to make this robot move? How do we know how much we have to push and pull on those tubes or rotate them in order to have a certain shape? No worries, I'm not going to get into any equations and continuum mechanics here, but I want to give you an idea about the challenges we have in mathematically describing what this robot is doing. From what we know from conventional robots that are made of rigid links and joints, what is usually done is we can use geometrical relationships because the links are rigid and we know how much a joint has been moving a certain number of degrees, and so we can pretty much compute where everything on this robot is. We could leverage this concept in continuum robots too by just approximating the robot with a couple of linear links, which would obviously be feasible, yet quite an approximation and only kinematic wise, because we would not look at any forces acting on the robot and would probably also not be able to reflect any of the flexible and elastic properties of our robot. So what we have to do in continuum robots is quite different from what we know from conventional robots. One idea that has been followed by a multitude of researchers is that we approximate the robot by a series of constant curvature arcs in space. An arc is characterized by its length, its radius, or curvature, and the bending plane. And so you can think about adding multiple of those after one another, such that you could approximate the shape that a continuum robot has. By me saying approximation, you can already guess this is also not the most accurate way to do it. Particularly, it can have issues when the robot is subject to any external loads or external forces because it interacts with the environment. So this is really super useful when it's used in free space. But once we move to a real application where we have interaction with the environment, we need to be more sophisticated in modeling. And the most sophisticated model today really describes every point along our robot in terms of its position and also its material orientation. This is the so-called variable curvature model that I depict over here. Now, by representing the robot by its position and also its material orientation along its length, we can then also embed all the phenomena that this robot is undergoing through, like the elastic deformation that it's experiencing is going to put small strains on its backbone. And so we can model this robot as a beam, which is undergoing linear elastic deformation, where the stress is experienced by the backbone, and it's linear proportional to the strain. The change in state can then be completely specified by keeping track of the orientation of the material prior to its orientation before deformation was applied. We can relate those through strain variables, use continuum mechanics, and particularly the Kurzweil theory of elastic rods to establish an explicit set of differential equations that we can then solve for the shape of the robot. Obviously, the complexity rises when I go from the conventional model in robots that I know towards this most sophisticated model of a continuum robot. But with this rising complexity, the accuracy also increases because I am including phenomena that are subject of my robot, that my robot is subject to. Luckily, we and our fellow continuum roboticists around the world have made significant progress in modeling over the past decade. We achieve a reasonably well accuracy. Let me tell you what that is. We can see two of the robot types here, this tubular continuum robot, world's smallest, and this tendon-driven continuum robot that we have been seeing earlier. And down here, I have plotted the error that I observe at the tip of the robot and the occurrence of this error over a certain set of experiments. Here we put the tubular continuum robot into 80 different possibilities of how to rotate and translate the tubes. And then we have looked at how well can this model estimate where the tip of the robot is. And we see there's quite a peak over here in the 1 to 2 millimeter region. And we can also see that for the tendon-driven continuum robot, this error distribution looks about the same. Bottom line is that the model has an accuracy of about 1.5 to 3% with respect to the robot length. So for example, if the robot was 300 millimeters long, the error at the tip becomes about 4 to 9 millimeters, which is reasonably well accurate. For comparison, the industrial robots that are used in automotive industry are usually an order of magnitude more accurate. Yet, this is the best we can do because it's much more challenging to model these robots. Now, rather than trying to model the physical effects which constitute the motion of our continuum robot, we have recently started to investigate how machine learning approaches can help us to improve the modeling accuracy. Rather than trying to physically model everything, we are now using data that we collect from our robot. For example, we observe where the tip of the robot is in 60,000 different cases by just using a sensor that we put at the tip of the robot, measuring its location in 3D space. And then we put this into a feed-forward neural network, a machine learning method, and see how this relates to the actuation parameters. For example, how much we pull on the tendons or how much we push and rotate the tubes. And by putting this amount of data through this neural network, we were able to show that the accuracy of this estimation of where the tip is actually becoming better. It's now below 1%. And this is probably due to the fact that this machine learning approach is implicitly considering all these effects that we haven't been able to model yet. For example, friction. Estimating the force acting on the robot's tip is also really important, and we have also tried this machine learning approach by using the robot as a virtual sensor, putting a couple of different forces at the tip, measuring using a camera system where the shape is, and feeding our neural network with this information to estimate what was the force that the robot was experiencing, and also achieved quite remarkable results here. In general, we are starting to explore these data-based approaches more in order to understand how well could this robot be governed by a model. Now, coming back to my favorite animal, the elephant, and looking at this baby elephant, this is pretty much how I feel about us continuum roboticists nowadays in terms of mastering the motion of our robot. I pretty much feel like this baby elephant, this can barely control where its trunk is going. And the problem is really with these continuum robots that we have been building and that we have been modeling, the possibilities of motions that these robots can perform are huge. They have some great properties and motion capabilities that can be leveraged and become unique for some of these applications, such as non-destructive inspection or surgery. On this slide, I'm summarizing some of these motion capabilities. For example, our robots can do a so-called null space motion. Keeping the tip where it is, we could change the shape while the tip stays at its place. Or we can enforce some of the shape of a continuum robot to stay in place while parts of it are allowed to move. Or we can use the robot to avoid obstacles. For example, as you can see here, this tendon-driven continuum robot moving very accurately in between these objects. And over here you can see, sorry for that, you can see that the robot is performing a so-called follow the leader motion, a maximum constraint on its motion. It is following a certain path and attains a particular shape, which is unique and can be described using our model beforehand. Now, while we are studying these motion capabilities, a huge challenge that we still have, and that's why I'm feeling like this baby elephant, is now that we can plan for these motions and use the model to evaluate the possibilities of motion. A question is how to get this pre-planned motion or this desired motion onto our robot. So how can we make the robot actually perform these motions? How can we control the robot such that it pulls on the tendons, pushes and rotates the tube in order to achieve them? The challenges we face as being a baby elephant is that we are having a nonlinear system, right? So the number of kinematic degrees of freedom approach infinity, which makes it really hard to be mastered. Secondly, we are facing an under-actuated system, such that while this elephant is able to use these 40,000 muscle fibers in groups, for us, it's not possible mechanically to recreate this. So we are facing the challenge of the impossibility to actuate all these degrees of freedom independently and simultaneously. And probably the biggest challenge from my perspective is that these continuum robots are ill observable. It is almost impossible, as they are so small, to obtain sensory information on all the degrees of freedom. Remember, I've been mentioning when we're looking at where the tip of the robot is, we have been putting a small electromagnetic sensor in this case at the tip of the robot, just measuring this one point. But now looking at this robot here, right, we would really not only want to be able to measure where the tip is, but it may be really important to know where this entire shape is. Envision this robot being within a human body. We really want to know accurately where it is. So knowing where it is, you may be like, why do we need to know it? We can model it, but the model had some errors, right? Even though we can get it down to this 1%, it's still a couple of millimeters, which might be too much depending on our application. So finding suitable sensors to give us feedback on not only one position on the robot, but multiple positions is still an open problem because my robots are too small and many sensors are simply too big. I've mentioned electromagnetic sensing as one possibility, yet they have a limited range. We're often using cameras in our lab to perform benchtop experiments, but as these robots are foreseen to move within some objects, we won't have cameras to be able to see through. Another thing that we could use is optical fibers with fiber Bragg gratings, for example, to obtain discrete strain information, which could help us to then reason about the shape. But still, this being ill observable is really an issue in terms of controlling these robots. Yet we are not really where the baby elephant is, right? So we are a little further than the baby elephant I've been showing you. We have advanced quite a bit. And what we mostly do is that we cheat by using a human in the loop. Rather than thinking about these sensors, which are not there yet, we are using the human as a master for the robot. We are using the robot in teleoperation. So the human gets an input device like this pen-like stylus over here to command a motion that is then reflected on the robot using the model that we have. And you can see how this tubular continuum robot you have seen earlier is now orchestrated by the user and performing the exact same motion, which is great because the human can account for all errors that we have in the model. If the robot is not perfectly moving to where it needed to move, the human will very likely adjust the orchestration, adjust how it's commanding the robot. And so we can account for some of the problems we see. Now, in the last part of today's talk, I would like to speak about the huge potential of continuum robots. I'd like to focus on surgery here. I have been fortunate enough to work with a couple of great collaborators. And while a lot of the research I have been presenting earlier in the talk is following a bottom-up approach, like focusing on fundamental findings, methods designed for continuum robots, when I'm looking at surgical applications, we almost always naturally come top down. We talk to medical doctors, show them about the capabilities of our robots, and then they get very excited, and we can then also approach the continuum robotics research from the top, thinking about applications. These are just two examples from my career, which have been mostly performed at Vanderbilt University, where I was fortunate enough to work with one of the pioneers in continuum robotics. About 10 years ago, which were concerned with transnasal surgery and intracerebral hemorrhage evacuation. In transnasal surgery, we were interested in using a continuum robot to enter the center of our brain to remove tumors through the nose on an almost like straight path and then curve at the very back end to remove this tumor using a continuum robot. We have been building a prototype back then that has been inserted through a single nostril all the way back. There's just one sinus you have to pass. You drill a little hole, and then this robot can really enter through this little hole, entering the center of your brain to remove pituitary tumors. And on the other side, we see this intracerebral hemorrhage evacuation, which is concerned with sucking out blood after stroke. For example, if a blood vessel bursted within the brain, a continuum robot could be used through a little burr hole on the top of the skull. It could be inserted. It's as small as a needle, right? It could advance to the hemorrhage. Here, this is just a silicone hemorrhage that we have been building with some gelatin inside to prove our concept. And we have been able to show that this robot is able to suck out the blood almost automatically. Now, this has been some great advancements, not yet in surgery, or like still on the benchtop and in ex vivo experiments. We have also been working on microsurgical targeting applications where the robot can be used as a third hand for the surgeon. This is a collaboration with Leibniz University Hanover, together with Professor Kahrs, who happened to be my husband. We have been working on integrating the robot with a surgical microscope, as it is often used in neurosurgery, for example. And you can see over here, these are some targeting experiments we have been performing. No worries, this is no brain. This is just a regular chicken breast from the butcher. You see, this is part of the microscope. It's a binocular vision component that can observe the surface of our chicken breast. And we have been marking some target locations. And you see the robot is moving through these target locations by visual surveying, by using the feedback from the surgical microscope to steer the robot into the right direction automatically. And we have achieved quite remarkable results here. So the error in this robot getting to this desired position that we have been marking was below 0.2 millimeters, which is quite amazing and very encouraging for us to follow this, this approach further. And as my last example, I also wanted to tell you about a collaboration that we did with the medical school in Hanover, Germany, over the past 3-4 years, where my PhD student, Erna Amanov, and Professor Florian Imkamp, a urologic surgeon, have been thinking about building a continuum robot, which would not need to access laparoscopic surgery through multiple incisions in the abdomen, but rather through just a single incision at the navel. And then this continuum robot being able to bend and turn around can be used as a base for further continuum robots to perform surgery, for example, on the kidneys to remove a tumor. This would greatly reduce invasiveness of the surgery. And during his PhD work, Anna built this robot prototype that we're seeing back here. By now, you know more about continuum robots. So this is a tendon-driven continuum robot, as you might be able to tell. And you can see it has 3 segments, 2 shorter ones in the beginning and a larger one at the back to steer. And then here, you may also be able to recognize the scale sheath for the variable stiffness from earlier that has been integrated with this robot. Then it has been built in a way that it can be sterilized and mounted to the actuator part, which has all the motors that are pulling and pushing on the tendons. And then this robot can be used as a flexible endoport in laparoscopic surgery. I want to leave you off with this vision of mine, how I see these robots being used in the future of surgery, for example. This is a small scene of the movie Transcendence. And you can see what the authors envisioned is actually continuum robots. There's multiple of those, 6 in total, that are getting into this severely injured human through multiple keyholes, performing surgery, performing interventions, commanded by artificial intelligence advancements. Here it's Johnny Depp in the computer controlling the robots as the artificial intelligence. But you can probably see just from this movie where continuum robots might be heading. They might be able to work with surgeons hand in hand, or even replace surgeons when they try to access locations in the human body that were inaccessible before, or only accessible by making a large incision, for example, at the head or at the skull. This brings me to the end of my talk. I have been very fortunate to work with brilliant student and postdocs and colleagues over the past decade, some of which you can see here on this slide. And it's really their hard work and their dedication that led to all the innovation and advancement that I was able to present about today. Lastly, I would also like to acknowledge the funding agencies that make our research possible. You can see them on top of the slide. Now, I have been moving to Canada last year. I just started at the University of Toronto last year, joining as an associate professor. So I'm still actively looking for new collaborations and more importantly, for ways to fund the bright minds that work with me at the Continuum Robotics Laboratory. Thank you for your attention. I'm now looking forward to your questions. Welcome also live, everyone. I hope you enjoyed my talk, and I look forward to answer all the questions that you have been posing. The first one I'm taking is, are you designing these robots with other tasks in mind besides surgical use? Absolutely. I just happen to focus on surgery today, and there are many other tasks. Like some of you probably had some ideas as I was explaining continuum robots. Another important task that we always have in mind is non-destructive inspection of expensive goods, of capital goods, for example, in airplanes, inspecting the jet engine after flight or regularly. It's quite a tedious task to look at all these individual turbine blades to make sure that they have not been impacted and there's no potential break. So that would be a great task for a continuum robot. Pretty much any non-destructive inspection task could be performed by a continuum robot that could sneak in a complex object to see if everything's right. Second question that I got, could these robots be the prelude to improve prosthetic body parts? That's an interesting question. I myself have not been focusing on prosthetics, but there's definitely some work in continuum and soft robotics in this area, because certainly the softness of a continuum robot and the elasticity can be favorable because the prosthetic component would probably be lighter. So yes, there's definitely work going into this. For example, there are people building soft hands. And also I have seen some like lower arm prosthetics that use a continuum robot style design. It's interesting. I have sometimes also been wondering about, does a prosthetic arm, for example, need to look like a human arm? Couldn't it also be like an elephant trunk-like structure? Because an elephant can also hold on and grab around objects. So yeah, definitely prosthetics is absolutely also could potentially benefit from continuum and soft robotics research. I just don't happen to work on this because I'm focusing on the smaller scale continuum robots. Okay, the next question is, have you looked more directly replicating the muscles, for example, in an elephant trunk? Not personally, but there has definitely been a lot of research in the continuum robotics community. Many have been using like artificial muscles, pneumatic artificial muscles, but it's by no means close to resembling these 40,000 muscle fibers in an elephant trunk. That's rather hard. I saw another comment of one of you saying that, oh, you could potentially also use 3D printing to build muscles. And that's also absolutely interesting. I'm observing this somewhat closely because I have recently, a year or two ago, I saw a research group that are printing heart muscle with a 3D printer, and it was amazing. So they could build these tiny patches of heart muscle and it would actually start beating at a very low scale, like by no means a real heart. So the problem is really the scale. To build a robot, it needs to have a certain length. And so I think we're not there yet, but that's definitely something that, that we're looking at. Next question is, do you collaborate with surgeons or medical researchers directly to see how your robots might help them with their work and then get their input on future prototypes? Yes, it's a constant balance though. Like I started off my career in continuum robotics, focusing more on that like top-down approach. I have been working during my postdoc time exclusively with surgeons that informed my research. But during this top-down approach, I realized, oh, but there are so many fundamental questions that need to be solved. So then I kind of turned away from that top-down to bottom-up, working on fundamental questions, which are usually harder to fund because there's only so much funding you can get for fundamental research, particularly in Canada. So there's always the need to also come at it from a top-down approach. So we constantly interact with medical collaborators. I'm constantly seeking for people that are excited about our research. And I'm fortunate, like pretty much any surgeon, for example, that I have been showing the capabilities of our robots have been like super excited, and they come with so many great ideas on how those could be used. So yeah, definitely working with both ends of the spectrum. Next question is somewhat related. How far are we from practical applications of these robots? Well, I guess in general, there are actually continuum robots that are used nowadays. For example, in medicine, there are robotically steered catheters. And these robot-steered catheters are simpler versions of continuum robots that, in a way that they have lower degrees of freedom. For example, they are only like rotating and translating a catheter, and the tip can bend. So that is a continuum robot per definition. So those are actually used in medicine. At the downside that a catheter can only operate within a vessel or vasculature. So they are relying on the interaction with the structure they're operating in, so they cannot operate in free space. That's why our robots are a little better. But there are definitely also a lot of efforts on getting these robots into the more sophisticated continuum robots into practice. For example, the Canadian company, even Toronto-based, Titan Medical, they are working on a minimally invasive surgical robot system that utilizes some of the methods I've been showing today. So they are using continuum robots in their system. And there's also some startups like Virtuoso Surgical in the United States that was founded by who happened to be my postdoc advisor, Bob Webster. So there are definitely these robots are on the verge to getting into the market, at least in this teleoperated mode where the user would still be in full control. It was also interesting to see, maybe you remember the OC Robotics, a very long, large continuum robot I showed very early on in my talk. OC Robotics is a UK company that was acquired by GE Aviation. So they are potentially going to use this robot in aerospace industry. So we'll see where that is going. But in case your question was targeted towards, in terms of my research, how far away is it from practical application? Well, we contribute, right? It's like contributing a little bits and pieces to the overall knowledge about continuum robotics. I'm certainly open to any collaboration to get this work out. We are applying for a lot of patents as well. We are in constant search of companies that would like to support our research, that would like to collaborate with us to get these things out the door. I'm educating the next generation of roboticists. I'm pretty sure some of them would like to maybe work in a startup or get some of those ideas off the ground and running. So that's all very exciting. Next question is, when we put the tubular robot in a human body, how can we reduce the friction to work well with our body tissue? I see. The tubular continuum robot is elastic. I am actually more concerned about the friction in between the tubes rather than the friction between the tubes and the body, because it's not so soft. But yeah, in terms of working well, it works remarkably well. Like, I mean, we have been pushing it up the nose to get to the brain. We have been using it in all different sorts of body parts. The friction is not the issue. It's more the, how can we sense the contact? So some of the contact may be okay because it doesn't disturb the task of the robot in that sense that it doesn't deform it too much. But yeah, in case that the contact happens and we are not able to recognize it, that could become problematic, right? Because even if the operator is teleoperating the robot, it might as well happen that while the operator is focusing on the tip of the robot and that the tip is doing what he or she wants, that the body of the robot is interacting with the environment and is pushing against something that it really shouldn't push towards to. So this contact recognition is really the issue, which kind of relates to the next question I'm seeing, which is, such robots would require an optical system with light and lens if working in closed spaces. Can you incorporate those with today's technology? This is an excellent question. I touched a little bit on the sensor challenges during the talk. In terms of integrating an eye to the robot to see what's happening, yes. So there are very small cameras available, so-called chip-on-the-tip cameras. They are like 1 cubic millimeter in size. So yes, we can incorporate those to the tip, and also LEDs made it a little easier to incorporate also light at the tip. Yet that sounds better than it is. So usually the resolution of these cameras is pretty limited. It's not as great as our HD that we usually observe these days. But yeah, there are small enough cameras to integrate, at least at the tip. So yeah, that's possible, but still needs some research to use this, yeah, not so great image resolution to still be able to do something meaningful. Next question is, are all of your prototypes controlled via computer? Can they be controlled remotely? I'm not sure if I'm understanding the question 100%, but yes, they are all controlled, like they are not autonomous in that sense. So they are still hooked up to a computer. There's still a connection. And they can be controlled remotely also. When you think about these control commands that are wired, they could also be transmitted wirelessly for sure. Meaning, if you think about remotely, right, there could be an operator at one hospital and the robot being in a different hospital, for example, and the teleoperation command could also be transmitted via the internet or via 5G. For sure, that's doable, like the typical teleoperation scenarios that have been worked on. So that's certainly doable. Next question is, could there be any application use of continuum robots in sustainable agriculture and landscape? Oh, that's an interesting question. There's definitely some work for a little larger continuum robots than those I'm working on. For example, in terms of agriculture, for example, for harvesting, there are these like soft finger hands that are so flexible that they do not need to exert a lot of force, yet can hold on to also delicate objects like strawberries, apples, pears, peaches, you name it. So in that sense, yes. I'm not aware of in what extent they could be used in sustainable agriculture. So no, maybe that's a good thing to think about in the future. I should certainly do so. So in case the question asker would like to get in contact with me, I'm looking forward to learn more about what idea you had. Last question that I see here is, what inspired you to get into continuum robotics research? Ooh, that's a good one. Well, I have been an elephant enthusiast, that for sure, but that didn't start off my career. I was at Karlsruhe Institute of Technology doing my PhD in surgical robotics. So I used a serial robot arm with a laser at the tip to cut human bone. This was awesome. It was a great research, but this robot was huge. It was an industrial style robot from automation that was repurposed for use in surgery. That's kind of where surgical robotics also started. And I always asked myself, is it really a good idea to have these huge robots around humans? And then I attended a robotics conference in, I think it was 2008 in Japan. And I saw a research presentation by a professor, Robert Webster, talking about these tiny continuum robots. And I was so fascinated that I couldn't stop thinking about what great impact these robots have. And for me, it really felt that's at the forefront of robotics research. This is really pushing the boundaries of what we can do today. And when I was looking for opportunities after finishing my PhD, he happened to look for a postdoc researcher. And I applied. Fortunately, he took me on, and I had a great time. I was there from 2010 to 2012, and then started off my own career eventually as a professor. So yeah, that excited me, and I'm excited about continuum robots on a daily basis, because I just feel it's really cool also for all the students that I'm working with. It's just really engaging to know we are working on something that not too many people are working on. So it's a rather small community worldwide. And we are really pushing what can be done in the future. And that's just really very fulfilling to me. I hope that answered the question. Last question. What do you think the new Continuum Robotics Laboratory means for the robotics industry? What kind of impact are you hoping that the laboratory has on future research? Oh, well, I hope that we are going to be the #1 laboratory in the world, that everybody's looking to us and saying like, wow, they are really advancing. They are really pushing forward with their amazing ideas. Being at the University of Toronto to me really means that I have access to all these amazing, talented students. Like just in the first 1.5 years that I'm here now, I am overwhelmed by how smart of students we have and how great graduate students I can recruit. I get so many cool postdoc applications. If I just had enough funding to get more postdocs also here to Toronto, that would be awesome. So I'm just hoping that we can kick something off great. I would love to see a couple of companies spinning off the Continuum Robotics laboratory in the future from some of our graduates. Just making Toronto in general being a robotics hotspot. You've probably been hearing, like, I mean, we have been building the U of T Robotics Institute that formed last year. So about 20 faculty members, so 20 professors working on robotics in Toronto, which is amazing. That kind of gets us at the very top level worldwide. And I just feel that Toronto may become the next big hot spot for robotics research in general. All right. Thank you all for your questions. Really enjoyed answering those. I hope you're having a fantastic evening if you're in Europe, and wherever you are, have a great, fantastic day, and don't let COVID get to you too much. Stay positive. We're getting through this together.
Thank you all for listening today, and I hope you'll tune in for our other U of T Where You Are lectures. In the meantime, I hope you'll check out the wide range of other programs on the Alumni Hub. Please let us know what you thought of this presentation and from where you were tuning in. In closing, best wishes from all of us at the University of Toronto. Keep well, and we look forward to seeing you soon.